Going to be talking about bridging today. Quick intro about myself, and then I'll follow out about what the point of this conversation is. I guess to start off with, bridging is kind of a problem that found me more than a problem that I was looking for when I actually first joined the space in 2020. Actually, I might just take this off. When I first joined the space in 2020, I was working at Tendermint, and the first thing I was actually working on was light clients for IBC. So before I even knew what the problem was, this is what I was working on. And then fast forward now, I'm working at Celestia, and I thought my bridging days were over. In fact, bridging seems to be a very important problem to be solved in the roll-up space as well. So I'm back there at bridging, and now I kind of want to give an update because Celestia has been thinking about this a lot with the sort of lazy bridging and project at the moment. And so I'm trying to present what the sort of latest mental model around that is. I'm not going to be as probably product-centric as the previous conversation, but I do want to sort of start there at the user here actually being the developer. So I think the first sort of part of here is the developer wants to build an app. I'm going to be more like roll-up focused naturally, but I hope this sort of applies more generally. And this developer kind of wants to find the sort of easiest path to make sure the assets from that user, wherever it may be, can be quickly, securely, and cheaply onboarded to their service, whether that be like a lending protocol, it could be a game, some sort of like ticket paying system. And there's a lot of choices out there. So this was a snapshot from yesterday. A lot of these are like specific bridges between specific VMs. Some are trying to be a little bit more general. So when we're thinking about solving this for the sort of roll-ups that want to use Celestia, we kind of don't want to reinvent the wheel. We're kind of trying to look at what exists currently instead of trying to make another protocol that people use. But there is definitely like a set of problems that we want to solve. I think the biggest one here is sort of security. So the current landscape, and we'll get onto this now, is one that uses sort of like multi-sigs. We're kind of focusing more just on the speed and cheapness, and multi-sigs are great for this, but something that we've been exploring is sort of like alternative options that can provide better security for people. So starting with my mental model here, there's like 4 terms. They're kind of very loaded terms, so apologies if they kind of mean a lot of different things, but I'll go through each of them and kind of like what each sort of component should be responsible for and what it should not be responsible for, and how we sort of like optimize for each to kind of give the best service for someone trying to build a roll-up or an application. So I'm going to start with the one that most people are familiar with. This is the transport layer. This is what people think of when they think of bridging. And it's basically how do you move you can think of token transfer, but generally more about like messaging. How do you move one message or send a message from one chain to the other? Most protocols are quite similar in the sense that they have 2 abstractions here. One is the sort of like security of it, so that just involves verifying the state of another chain. So chain A needs to have something to be able to verify the chain of B, and then vice versa. And then on top you have like the application logic. And a lot of this was designed in a modular way for different kind of like application logic. But there's really only 2 that I've seen in practice, the major one being transfers, and most of them have this like lock and mint paradigm. And then to go back the other way, it's about sort of burning and then unlocking. And so in that process, just to kind of go through it here, chain B needs to receive some proof that chain A has locked the asset before it mints it, and then vice versa, chain A usually needs to receive some sort of proof that chain B has burnt that asset before it can unlock it. The other one that I think is pretty powerful is, I'm going to call it remote account calls. I know in IBC it's called ICA, interchain accounts, and that's basically the ability to kind of like remote procedural calls control an account from another chain. So we kind of replace the signature verification as the authentication of that account, and rather we have some arbitrary verification. So the chain decides, okay, it could be multi-sig in this case, it could be something else, and then it commits to that action, proves that it's committed to that action to chain B, and then chain B performs that action on some account. So we can think about like liquid staking as an example. So then an account can like stake or redelegate. It could be various others. With Celestia, you can sort of like pay for the data, and so that kind of could be paid actually by an entire chain or entire rollup. So now moving to the second part is the actual like security. The sort of basic models we have here is an external multisig and a proof of stake multisig. I've kind of tried to divide the two because they do have kind of different properties here. So the proof of stake multisig comes from most of the L1s. The cost is really high here because you're running hundreds of nodes and they're usually based on some sort of stake. I put a little asterisk here because if you're doing that anyway, so not in the case of a roll-up where the DA is outsourced, you kind of get that part for free. But most of these are pretty quick in the terms of like, it can happen within like a block or two. So we're talking a couple of seconds. Relatively cheap, but pretty insecure. And this is the kind of status quo where we're relying on more reputation than we are on actual verification. And so this is when we get to the verification part. So the new kid on the block is ZK. Not too new, to be honest. It's been around for a while. And so the way we can use ZK, and this is a bit of a misnomer because we're not really using it for zero knowledge, we're using it for compression. So we're basically taking the same primitives, but being able to prove the state transition function from one block to another. So the way that works is we have a single like proof in which we verify the data. So in the case of like Celestia, you'd be verifying that these blobs were posted by Celestia consensus, and that's the data to be processed by the rollup. You apply some fork choice rule. So in the case of a centralized sequencer, it's like, was this blob signed by the centralized sequencer? You might have some other rules where you limit the amount of blobs within a block, or maybe there's some sort of validity predicate to this, and then you verify it. So in our sort of prototypes, we were using EVM, and so Succinct already has this RSP that we were using to verify the execution. And so in terms of like inputs to outputs, you're basically taking the previous verified state, the Celestia blocks, which represent the kind of the data, and then the new state. So these are all the hashes, and these go into like the public inputs. And so that way, the state of the chain of the other chain kind of slowly increments, and then we can use that state to verify the messages. So then when we sort of implement this and see how it sort of works in the wild, it kind of doesn't look too well in comparison to some of the existing stuff. So speed is a lot slower, so there's been a lot of work on trying to improve this. A lot of the proof generation is highly parallelizable, but still we're experiencing 5 to 30 minutes per proof, which is a lot more than the couple of seconds. And this is kind of very important for people that when you're creating a new application, that it's seamless for the users to get their assets across. So that's not good. The other thing is the cost. So if you're running a multisig, the cost of those like attesters that are attesting to state might be in the thousands, but maybe over a year, but perhaps over a year of like proving every single block, you're looking at millions. Of course, the benefit here is you're actually verifying all the sort of like execution of those blocks. So we're no longer having to rely on the reputation. We have this very succinct, small way. In the prototypes we're using graph 16, so only a couple of 100 bytes to verify from one sort of like arbitrary point in the roll-up state to another. So pretty good start, but still something lacking. And I think a lot of people are kind of waiting for kind of the algorithms to improve or for some sort of like hardware acceleration before we get to something that kind of competes with multisigs. But at the moment, there's a lot of people thinking that we're sort of still far out. There's another way we can do this, which is we can look at ZK fault proofs. So optimistic rollups kind of came before validity rollups did, or ZK. And so we use the ZK proof, or the proof of execution, not to prove that it's valid, but to prove that some attester incorrectly said what the state of the rollup was. And so rather than having to produce these proofs all the time, you only have to prove them when there has been some sort of malicious agent. And so the cost drops significantly. The speed kind of gets worse because now we're talking about days or maybe hours where you have a window to challenge. And the security now requires like an honest full node, someone that is capable of like executing the state, realizing that there is a difference between what another node has attested, and then challenging them. But you can kind of combine this in some sort of like economic incentive way to make sure that there are several nodes that are incentivized to produce attestations of state and to sort of keep each other honest. So that's the current like different set of security options at present. And so kind of putting this back in the transport here, like what are we looking for is a mixture of speed, cost, security, and I haven't really covered this, but it's kind of obvious as it's well connected, so that you can actually connect to all different kinds of chains. If you can only connect to specific ones, then that doesn't work because the user's assets could be anywhere. Okay, now I'm going to move across to advancing. I use the term advancing. I think there's a lot of like different language about this, and I want to be very specific about here. The idea is about advancing a transfer by having someone like fill it on the other side. And I'll explain this in a little bit more detail. Not to be kind of confused with solving. Solving implies that there is something to actually solve. This is actually like a deterministic transfer. You either fill it or you don't. So here's the example that I give here. So we have two chains. Alice wants to move 10 tokens across. And so what the Alice does is kind of locks it up. And there's this kind of receipt that's generated for that. And there is this condition essentially that someone needs to prove that Alice has been given $10 from, or 10 tokens from their account in order for them to receive that from the locked account. So the filler, I'm using 9 because there's some sort of fee that the filler gets for this. The filler pays Alice on chain B the 9 tokens, and then a receipt of that is generated, and then eventually when the filler wants to, maybe they can aggregate this over multiple blocks, we'll actually use an underlying transport. So here, like, you still need some sort of bridging. This can be either multi-sigs or ZK to then actually prove to chain A that they fulfilled the order and that Alice now has the tokens on chain B. So that's one way of doing this. Another way that has kind of been explored is instead of just having a single channel, is you have two different. So one is like kind of like a hybrid where you're combining a secure but slow channel with a fast and insecure channel. And there is a pool on chain B with those secure tokens. I'm just going to call them ZK for now. And so Alice sends it through the multi-sig, and there is a pool from the like fillers which can convert the multi-sig denominated assets into the ZK denominated assets, and then plus some fee to the filler that's provided the tokens in that pool, and then eventually that filler or this service kind of has to wind it back through the chain A, through the multi-sig, and then back out through the ZK version to fill up that pool. And so they get paid for doing that. And so for roll-ups, there's kind of this trade-off here where you've now got things that can happen instantly, but only so, but you kind of have to sort of, there's a cost with that. So you have to make sure that you're incentivizing these people to fill the other side of the transaction. And so they're only going to do that if there is enough like fee for them. And so if there's a lot of volume, then it makes sense. If there's not enough volume, then you end up paying sort of a lot more. But there is one thing that can like help with this sort of like capital allocation problem is if you have like a DA layer, especially one that is like relatively quick, you can keep those tokens on the DA layer itself, and because the rollup has to verify the state has to verify the consensus of the DA layer anyway, they already have access to the state, and this means that you can bridge within one block from the DA layer to those rollups. So what the filler can do is they can see an order moving from one to the other, and they can quickly push out that asset to that chain and fill that order without having to have it live there for a long period. So this provides some sort of like advantage in terms of like capital allocation. But going back to the model now, we can kind of use advancing for speed and not so much have to worry about that in the underlying transport layer. So for some, the underlying transport layer can be quite slow as long as it's secure and cheap. And there are like other mechanisms that we can use to advance the transfers. So if we go back to the sort of table I had beforehand, this kind of makes ZK far more feasible, far more appealing than the other sort of like models. So we can have one where balancing that these fillers need to do, all these other stuff happens kind of slowly and in larger bulk amounts. But as far as the user's concerned, the assets move really quickly and they have the exact same security guarantees. I think, importantly, this is not just about one protocol replacing the other. I think if you're trying to build good sort of protocols at the transport layer, you need to provide optionality. You need to make, there might be some users that prefer to have, if they're sending like a low amount of tokens, to actually have low security for the cheap, quick sort of route. So in that case, multi-sig is so valuable. So it's about keeping sort of optionality for people. I'm going to now jump across to routing. This is a term that I know is used elsewhere, maybe for routing between different DEXs. In this case here, I'm sort of meaning it as partly an aggregator. So this is something that can take users' preferences, and this could be, I want to send a token from chain A to chain B, and I care about security, or I care about making it cheap, and it presents the path to get there, the transaction to sign. And so this router in many cases is there to provide UX. So when I'm building the front end of my application as a rollup developer, I basically just need to connect with this router, and this will help find the assets where the users have them, and then find the best path. And there are versions of this solution which are off-chain and based on reputation, and then there are versions of this which are sort of on-chain. So this is the responsibility of the routing is to improve the UX. And so we have this abstraction here where the transport isn't worried so much about the UX, he's trying to give as much options as possible, it's supposed to be permissionless. And where we actually get that good UX is from the routing, which is between the application's app and the actual transport layer. And it's trying to do all the aggregation, it's trying to work out where all the users' assets are, and trying to do all these graph problem calculations. This is also known as solving, and I did want to acknowledge that as well. So a lot of people use that. Solving usually implies that their transaction is partially filled, and some solver needs to compute what the actual solution is. So that could be to go through this route or that route, or through one DEX or another, from one token to another. And that brings us on to the next one, which is asset fungibility. So I think there are a lot of teams which look at asset fungibility and think it should be solved at the transport layer. In short, asset fungibility is because there's different security assumptions when you go from chain A to chain B to chain D, or from chain A to chain C to chain D, you have two different token representations. It's also the same case if you're using two different security models, or if you're using a multi-sig, or if you're using ZK or ZK full proofs. They should all be different denominations to represent the different security. And that becomes a problem for users because I just want the USDC to move to my application. I don't really want to have to handle all the different kind of denominations of this. And so there are some teams which are looking at sort of combining all the different bridging risk into a single together. So just having, for example, a single collateral token for multiple synthetic tokens. But I think that shouldn't be solved at the transport layer. This is something that should be pushed up to the application. So I think there are some things that the application, complexities that the application should be aware of. And in this case, I think they should be the ones handling denomination. We shouldn't be trying to do it for them. Once again, we should be focusing on the transport layer to be permissionless, to give them options, and they can decide whether they want to combine the different token denominations together or whether they want something else. And I actually talk about the routing here because this is the option to sort of impose some sort of rule around how assets move around. I give an example here, so you could say the asset must be the most secure connection from the asset issuing chain. So rather than having, I'm going to give the example of Celestia, so TR on Celestia, rather than going from Arbitrum to base directly, it must flow through Celestia, and that way you can keep the denominations all the same. Of course, that adds an extra hop, and now we're thinking about multi-hops, which is something the Cosmos ecosystem has thought for a while. But that way we can make sure that it's all the same sort of denomination, the same sort of security assumptions, And if we're using this model of having advancing or filling, we actually don't worry about the speed. So it can jump around a little bit more. That's okay. So I'm going to add that to the routing part as well. The last thing now is back to the transport, is this idea of just signing once and being able to perform the action you need to perform. So when, especially going back to the previous case, if you're trying to move across multiple different chains or multiple different environments, you kind of want to have some way where the user only needs to sign once. They shouldn't have to sign for every single sort of hop. And so in this case, you want some sort of atomic composability where you have transaction 1, some sort of validity predicate that transaction 1 was successful, and then execute transaction 2, and so forth. And this can actually lead to some very powerful things that I think we should be working on, which is removing the deposit button. So often when you open a new page or a new application, say it's a game, there is this flow of like moving your assets across as like a deposit. If we can have sort of atomic transactions cross-chain, what we get is the user, and say this is like they're on an application which is a lending protocol, they can just hit supply the pool, and the backend already works out, okay, they need to move it from this asset that they have on some other chain to here, and then perform that action. So they can group these together, and it make this appearance that all the state is can be seen from the user, like it's as if it's already on that chain. So this part of sort of composability, and I think that's a sort of major thing to also solve on that transport layer. The last thing, which I haven't really talked too much and isn't so much the point of the call, is the authorization. So this is kind of like the wallets. So once the routing has provided these transactions to perform the action that the user wants, it's important that you have something that can sign over it and actually provide clearly, like human readable, what they're actually doing. So this is where the verification comes in. We need to have some way in which we can verify that the actions that the user has been told that they want to do is actually correct. And so this is the kind of like mental model that I have when it comes to bridging, like how we can improve the sort of developer experience and make it easy for them to set up their like rollups, for them not to have to worry about how to create their own bridging protocol to make sure that assets can come in from any chain and where they might be. And that's the end of the talk. Thanks for your time. I was told I had to put a mammoth on here, so from marketing, so here's the mammoth.